What's up, Physics 20s? Mr. Jiggly here. Continuing with dynamics, so all about forces when we're talking about dynamics. Today we're going to talk about Newton's first law of motion, and in following days we'll talk about the second and third laws, but today we focus on Newton's first law of motion. So we all start off with a bit of history here. What do moving objects tend to do? And in early days, people used to think, well, they used to come to rest. They used to really like a natural state of rest. So Aristotle was the first person that we know of to put this into words, 4th century BC. He called this property of matter impedus. So he said things like to impede the motion, things like to have a natural state of rest, so anything that's moving will gradually come to rest. It was a long time later that Galileo actually started looking at the idea of inertia and saying that things like to be in whatever motion they're in, and they will continue in whatever motion they're in until an unbalanced force acts on them. And that's going through, and that's talking more about the idea of inertia. So things like to move the way that they move. Now, one thing to kind of note with this when we're talking about inertia is a property of all matter, property of matter. What it is not a force. And oftentimes you see test questions and different things, especially multiple choice test questions that go through and say, which of the following is true? And it says something wants to keep moving due to the force of inertia. If you see that, ignore it, scrap it right away. Inertia is not a force, it is a property of all matter. All matter likes to keep doing whatever it's doing in terms of its motion. So if we think about that in terms of this vehicle, I've got a vehicle that is going 60 kilometers per hour. If it is allowed to keep doing its thing, so no outside forces really acting on, no forces at all acting on, it's just going to continue moving at 60 kilometers per hour. Again, that object likes to keep moving. If an object is at rest, this is a Mythbusters, by the way, of that old magic trick where you pull the tablecloth out really quickly and everything stays put, just within a more extreme version with the motorcycle. But yeah, so what do objects at rest like to do? Well, they like to do what they were doing before, and they like to stay at rest. So object at rest likes to stay at rest. So we can explore this a little bit more. We've got this situation here, and some of you might be doing driver training, and some of you might, might be sliding around on ice because it snowed a lot the last little while here. But say this is you. I don't know why you're driving a convertible while there's ice in the road, but whatever. Say this is you, and you're driving, and you see there's a red light over this way, and you need to come to a stop. Right? There's a red car in front of you, but there's this huge patch of ice in the middle. You obviously want to stop your car, right? The ice is eliminating friction, though. So even if you were to hit the brakes, you typically continue moving with the motion that you're moving in. So whatever motion you're moving with, you continue moving with that motion. And it becomes very, very clear when we limit friction, right? So we put ice on the road or something like that. Now, ideally, this situation never happens to you, but hopefully you kind of get the idea. So that car wants to keep moving until it smashes into something else. Same sort of idea. So when we talk about the motion of something, there's the speed part of it, but there's also the direction part of it as well, right? So we're more talking about velocity now than just speed. So same convertible driving in the winter hits this patch of ice. Where would this car end up? Well, it's going to keep with its standard motion that it's got, or its regular motion that it's got, and it's going to end up in the ditch. Here's the, I don't know how to draw a car from that view. There's the car in the ditch. It's going to end up going straight through it. The driver obviously wants to turn, but the inertia is going to carry it forward, and in this case, hit the ditch. Perfect. Same idea, like you could experiment with this with, you know, Costco if you're loading up with a bunch of heavy stuff, like looks like you got ice cream, milk, huge cans of tomatoes, and a bunch of other stuff that I don't know what it is in there. So you're at the old liquidation store and you are pushing this gigantic cart around. Is it very easy to move that cart, to get it moving in the first place, to get it to go around corners, to slow down, things like that? Not so much. At the start of the shopping trip, though, pretty easy, right? When you get that empty thing. So one of the things that we look at with this inertia, this idea that things like to keep moving, it's very dependent on mass, right? So the more mass you have, typically the more inertia you have, typically the harder it is to change that motion. So Newton's first law, we haven't actually said Newton's first law yet. So essentially it's objects in motion like to stay in that motion, like to stay in that motion. And then we could even add to this a little bit. We could add in the absence of unbalanced forces. So in the absence of unbalanced forces. So we'll just kind of put that one up for the typing. I think you have this written out in your notes in a little bit here, but we'll put that one up and we'll kind of think about these couple different situations that we've got here. So when we mean the absence of unbalanced forces, that means all the forces are balanced or there's no forces whatsoever. So let's go through and let's think about this. This person traveling at 50 kilometers per hour for some reason is hitting a wall. Hopefully they're like a stunt person in a movie or something like that. They hit the wall. If they are not wearing their seatbelt, what is this situation gonna look like? So take a second, think about that one. You can put the video on pause if you need to think it through a little bit more. Some of you are probably already starting to think that, oh, and this is where I've got, hold the phone here, some very cool animations. Delete that. There we go. So here's sort of the idea. Assuming that the person is not wearing a seatbelt, look how slow that person up top goes, is not wearing a seatbelt, they're moving forward. They're going to continue moving forward until an unbalanced force acts in them. So for the motorcycle on the bottom, it is, let's see if I can draw on this piece. It's them skidding along the ground. It's going to slow them down. They're just going to keep on moving forward. For the person in the top scenario, it might be a little bit the windshield, and then again, sort of the ground over here as they hit the ground. So they keep moving forward until we see that unbalanced force. Let's see, I've got another little animation up top, and then a truck accident down there. It's very important to tie down your load. So the person up top doesn't have their ladder tied down. They obviously wanted to stop, but because they run into the car in front of them, inertia keeps them and keeps the ladder moving forward, and we see that it continues with whatever motion it was in beforehand. Perfect. So let's get out of this one. Let's go back into the one that I can easily write on. So second activity here is, what if you're sitting in a car and you're sitting there and the car is at rest and somebody runs into you from behind? That's this situation. Now you'll notice something very specific in this particular problem right here. There is no headrest. So think about that. Your head is a fairly solid mass sitting on top of your neck, and a car comes and hits you from behind, and there's no headrest. So the car is going to be forced forward, your body's going to be forced forward, but what about your head? So is there any force necessarily pushing your head forward at first? So here's the situation that we've got. You're sitting there, everything's all happy, you're maybe listening to the radio, and then the car starts to accelerate forward, and your head stays where it is. Let's go back and forth from this. This is whiplash, essentially. So your head stays where it is, your head is whipped backwards, and then eventually whipped forward as it catches up with your body. So your head is staying at rest until an outside force acts on it, or an unbalanced force, I should say, acts on it. Perfect. So here's the one that we were talking about, Newton's first law. If an object experiences balanced forces, in other words, the net force is equal to 0, it moves at a constant velocity, or in other words, there is no acceleration. We can, and this is something that's very, very, very important to know. Constant velocity means balanced forces. So I'm even going to write that out. Constant velocity equals balanced force equals F net of 0. Perfect. So something very, very, very important that we're looking at, probably the key idea for this particular lesson. So constant velocity is balanced forces, which means we have a net force equal to 0. We can also kind of look at this in another way. So I know that net force is mass times acceleration. So even just looking at our formula, this is a grade 8 formula. We'll kind of look at it a little bit more tomorrow, but just reminding us, our net force is the mass times acceleration. Our net force is also the sum of all forces. But if I have zero acceleration, so zero acceleration, that actually means that I have a constant speed or constant velocity. And if I have a zero acceleration, well, that means this whole side of the equation is equal to 0. That means my net force must be equal to 0. That means all of my forces must be balanced. So it's all coming together, even some of the things that we're talking about last unit and the last couple of units, talking about kinematics versus dynamics. So just kind of check this one out for a quick second. We'll have a quick look at this one together. So an object, and then we'll make you pause the video and try out the next one. So an object is moving to the right at a constant 4 meters per second. The fact that it is constant is probably more important than the 4 meters per second in this one, to be honest. But moving to the right at a constant 4 meters per second, it is being pulled by 170 Newton force to determine the friction or resistive force. Perfect. So we can probably assume it's not moving up and down. We can probably assume that the vertical forces are going to be balanced. That's our normal force and our force of gravity. They're going to be balanced, so we're not really going to worry about those ones too much. And you'll notice what we're doing here, actually, is we're drawing those force diagrams or free body diagrams, which are just beyond important for this unit. So it's the horizontal that we're really going to look at. So if it is indeed at a constant speed, we know, because it's at a constant speed, we'll annotate this one up here, we know that the net force is equal to 0. And in this particular case, we can go through and we can do this in one of two ways. We can say that the net force has to equal to 0, and I've got my applied force pulling it to the right, and my applied force, what was it there? It was 170 newtons. 170 newtons. And if my net force needs to be 0, well, then my friction force needs to balance this out perfectly. So my friction force, I'm going to make that about the same length. So my force of friction needs to be equal to 170 newtons the opposite direction. So we can use a diagram to figure this out, or we could go through and we could do what we did in the last lesson. We could say F net, well, that's the sum of all the forces. That's going to be my applied force plus my friction force. If I wanted to go through and solve for my friction force, I would say that's my net force minus my applied force. So just rearrange to solve for net force. And then I'd go through and I'd say, oh, well, that's just 0 minus 170 newtons, which is negative 170 newtons, or 170 newtons to the left. Same thing that we've got drawn on our diagram up there. Perfect. So that's not too bad, right? It's really not too bad. So it's a bit of space for me to work. Your example, let's have a quick look at this one. Let's try and figure this one out a little bit, and then I'll get you to put a pause and try it out. So we got a 250 kilogram car, that's our mass. It's traveling forward at a constant speed. Remember that constant speed means that the net force is equal to 0 of 60 kilometers per hour. So that's our velocity. It experiences 3 horizontal forces. So you got a forward force of 11 kilonewtons. Let's label that one. It's probably going to be our applied force. Don't want to call it FF for forward force because that looks like force of friction. We've got a force of friction, so a resistive force of 3 kilonewtons. Let's call that one FF for force of friction. And then finally, the force of air resistance. I'm going to call that FAR for air resistance. And then the question is, what is the force due to air resistance? So at this point, I'd put your video on pause. I'd start with maybe a free body diagram. It's a fantastic place, or a force diagram, fantastic place to start. Put your video on pause and see if you can figure it out. I'm going to do the same thing, and we'll catch up in a minute or two. All right, so I've started this out. I've labeled some of the really important things. My net force is equal to 0. I've started to make my force diagram or free body diagram with my 11 kilonewtons forward and my 3 kilonewtons backwards. Something that you'll want to look at here is the 11 kilonewtons is purposefully significantly bigger than my 3 kilonewtons backwards. I did not measure this. If you want to get specific, you can always get out a ruler. You can always make scale diagrams. But making it even a little bit to scale, so making sure that 11 is bigger than 3, will probably really help you out. So, knowing that my net force is equal to 0, knowing that I've got 11 kilonewtons forward, we can probably just reason our way through this. I need this to make 0. I need a pretty sizable force, not quite as big as my 11 kilonewtons, but I need a pretty sizable force going backwards. And lots of you are already kind of reasoned your way through this. If you've got 11 forward, 3 backwards, that means you need 8 more backwards, so 8 kilonewtons backwards in order for everything to equal to 0. So that's one way you could potentially look at this, is just by drawing a diagram and reasoning your way through. Again, the other way that you could look at this is by setting up your formula. F net is equal to F1 plus F2 plus 3, F3, et cetera, and actually solve for that force. So let's have a look at that. All right, so I kind of did the work there to save a bit of time for us. But essentially, if we're using the formula, we say F net is the sum of all forces. So F net in this case is the applied force plus the force of friction plus the force of air resistance. We are in a 1D situation, but we do have things going forward and backwards. So I made very, very clear here to, let's grab a different color to highlight a little bit, made very, very, very clear to set my reference. So I said right is positive, therefore left is negative. So when I'm doing F net is equal to the applied force plus the force of friction plus the force of air resistance, I need to keep in mind that my force of friction, because it's towards the left, is in fact negative. So I just included that down here as well. And then I go through, I rearrange, solve for my force of air resistance. It's equal to the net force minus the applied force minus the force of friction. 0 minus 11 kilonewtons minus negative 3 kilonewtons, which is, again, negative 8 kilonewtons. And negative 8 actually meant towards the left, so 8 kilonewtons towards the left. The same thing that we got when we reasoned things through with our free body diagram. Very, very, very good. Now, there are other ways that you can deal with this direction. So some people, I'll just do this off to the side. Some people really like to do F net is equal to the applied force minus the force of friction and minus the force of air resistance. So all they're really doing with this is plugging the direction right into the formula. So rather than plus a negative, we're doing subtracting the positive value. So kind of keep that in mind. There is more than one way to look at this, and it's really up to you what you want to check out and what you want to go through for that one. Perfect. So that's a bit of space for me to work. Next little section that we want to talk about is the idea of static equilibrium. So just checking out that definition, static means not changing, not moving, things like that. Equilibrium, obviously the key word in that is equal, and we are talking about forces canceling. We're also talking about the net force being equal to 0. Perfect. So whenever we see this idea of static equilibrium, all the forces cancel each other out, and the net force is equal to 0. Something is at rest, and it stays at rest. So one of the big ideas that we really see with this is like hanging signs and things like that. Right? And we'll look at a couple examples of those as we come through. So a definition that you need to know about is equilibrant. So equilibrant is the force that is needed to keep an object at rest, or in other words, the force that is needed to balance out the other forces. So keeping something at rest or balancing out other forces. Please do not confuse this with net force. Lots of people confuse these two, but they are not the same. So net force is not the same as an equilibrant. And I spelled that totally wrong. Equilibrant, slightly better. So keep it in mind, the equilibrant, when we're dealing with an equilibrant, the net force is equal to 0. Right? That's sort of a really, really big idea for this. So, a couple different situations to deal with here. Determine the equilibrant, F3 for this situation. So right off the bat, it's saying determine the equilibrant. I know that the net force is equal to 0. We could probably just reason our way through this. I've got 400 newtons towards the left. I've got 100 newtons towards the right. We need an additional 300 newtons towards the left. So my F3, just kind of reasoning our way through, is 300 newtons. And I may have said left. I definitely meant towards the right. So that's one way we could look at this. The other way is using the formula. I'm going to put it on pause to save a bit of time for us. But the other way is, again, using the formula. So again, using that formula, we'd go through and we'd say, okay, well, net force is the sum of all the forces. So F1 plus F2 plus F3. I rearrange and solve for my equilibrant, F3. That's my net force minus F1 minus F2. Again, we should probably make a convention for this, and we'll just use our typical sign convention. Right is positive. So it's 0 minus negative 400 newtons, because remember that 400 was towards the left or backwards, so we'll call that one negative, minus positive 100 newtons, which equals to positive 300 newtons or 300 newtons towards the right. So really not so bad there. Two different ways to look at the same thing. So far, everything we've done has been in one dimension. And you know that in one dimension, things are fairly straightforward. We just set up a reference system. So in this case, we said right is equal to positive, and then we just add things up. 2D situations are a little tiny bit trickier. The nice thing about this one is that these two forces are at right angles to each other, and when things are at right angles, we can typically just use tip to tail to figure things out. So the way that I like to figure out the equilibrium for this, again, equilibrium means that the net force is equal to 0, and we've got this third force that's got to balance everything out. So this third force. So I like to think about this, even though it's kind of not in components, we don't necessarily need components for this one. I like to think about it in terms of components. So part of my equilibrium, when I'm thinking about this equilibrium, part of it needs to be going towards the right, because part of it needs to cancel out F1. So I'm going to say F3 in the X has got to be equal to 30 newtons. So now we see in the X component, the F net is equal to 0. The other part of my F3 has to be canceling out F2. So the other part has to be in the Y component. So F3Y needs to cancel out 50 newtons down, so it needs to be 50 newtons up. Now, if I'm looking at those two components, my X component and my Y component, we can think about how we add those two together. Well, we add them tip to tail, and we end up with overall F3 going up at an angle kind of like this. Right? So if you were asked to actually solve for this, which we're not going to do for the sake of time right now, if you were to ask to actually solve for this, there's two things that you would need. You'd need to solve for the magnitude of F3, and you'd also need to solve for the angle. So make sure, and we've done an absolute ton of this in previous units, so make sure that you can solve for both of those two things and accurately describe that angle, accurately describe what F3 is. So that's not bad, right? Absolutely not bad. The other way that you could potentially do this is you could add F1 and F2. I'll just show you down here. You can add F1 plus F2. So here's F1, add it to F2, and we know that those two together are going down at an angle right here. We know that F3 needs to perfectly cancel that out. So here is F3x and F3y, essentially the same thing that we just did, right? So this one is 30, this one must be, 30 in the opposite direction. This one is 50, this one must be 50 in the opposite direction. Perfect. So as long as we're canceling out those other forces, we are doing great. One more little example. So what if the forces aren't at right angles? And if the forces are not at right angles, then we have to start thinking about components. Most of the work is done for us for this one, which is really, really nice, right? Like a lot of the work is just breaking them apart into components. So if I was given F1 and given F2, I would break them apart in components. I've got F1x, I've got F1y, and same thing already done for us on this side, F2x and F2y. Perfect. So, and when we remember back to these, the three steps that we had, were to break things into components. So every vector that we've got, break it up into components. We want to solve for the x and solve for the y separately. And then finally, we want to, with whatever we've solved for x and y, we want to make a new 90-degree triangle and solve that new 90-degree triangle. So I'm going to show a little bit more work for this one. I'm going to say f net in the x is equal to f1x plus f2x plus f3x, and we're looking to solve for f3, knowing that the net force is equal to 0, so that's going to be f net minus f1x minus f2x, and very simply that's 0 minus, let's go back up here, f1 is negative 40, newtons, and then we're going to subtract from that negative 70 newtons. So I believe that works out to be positive 40 plus negative 30, or plus negative 70. That's negative 30 newtons. So that's F3, and again, that is in the x component. Then I'm going to solve for my y component. So my net force in the y component is F1y plus F2y plus F3y. F3 in the y component is F net minus F1 minus F2, of course, all in the y component. We can plug that in real simply, so it's 0 minus, and these ones are both positive, so minus positive 50 newtons, and then minus positive 30 newtons is just negative 80 newtons. And we forgot a 0. Negative 80 newtons. There we go. So F3y. Now, if I wanted to solve for what F3 actually is, my very, very last step here, if I'm trying to solve for what F3, I know that F3, well, part of it is in the x. So F3x is, what was that, 30 newtons. And you'll notice that I'm no longer including the negative because now we're back to 2D. And I know that my y component, so F3y, was 80 newtons downwards. And again, I'm not saying it's negative 80 newtons. I'm saying it's 80 newtons downwards. The downwards comes from the arrow that we see here. And then overall, I've got F3 coming down at an angle like this. And again, you would be expected to be able to solve for F3 using Pythagorean theorem. And you'd also be expected to solve for the angle using a little bit of trig. In this case, I would use tan function for that. So there is the lesson for today. Lots and lots and lots of big stuff in there. Make sure you do a bit of practice. Obviously, watch the video. You can look back and check out the video if you need to and put it in a pause and do what you got to do. And let me know on Google Classroom if you need any help with anything. Talk to you later, Physics 20s. Bye for now.